in mirror symmetry when you especially try to implement the SYZ program and build mirrors of symplectic manifolds in the presence of integrable system structure from non-Archimedean spaces that are defined locally in the base, or maybe non-commutative non-Archimedean spaces that are defined locally in the base. So you really have to tackle this descent problem, this gluing problem. And so we came up with a setting which at least applies to the gluing of the type of covers one gets in the SYZ picture, and hopefully will be exactly what one needs. But the main result, I mean, the setting is coming from this approach to gluing that that you need to compare to the standard descent in algebraic geometry, and the main result is really about comparison with the standard descent in algebraic geometry. But the formulas one gets are really the ones one would like to apply to mirror symmetry considerations and to non-commutative geometry in general. So the idea, the goal really is to have some flexible enough descent formalism. Concoct descent formalism for sheaves on analytic or non-commutative spaces. They could be actually commutative too. So for sheaves, without resorting to generators. And so, in particular, this would be useful to do if you want to have description of equivalences of categories of sheaves in non-commutative geometry when you don't have generators. So Fourier-Mukai transforms, and also when you try to do deformations or homology theory, or you try to understand the analytic theory. So this is the goal, and let me just recall the basic premise of this categorical non-commutative geometry. Yeah.
In what way does descent usually use generators?
Yeah, I mean, it's a technical thing. I'll get to it at some point, but the idea is that, you know, you write your space as an atlas module relations, right? And then the descent statement is some kind of a Barbeck theorem, saying that you have a coidempotent comonad whose modules are the sheaf theory. And this is really a statement about generators, because, you know, your atlas is given, yeah, exactly. Your atlas is given by some affine space. You have generators, and then okay. So what's gonna, yeah, so you'll see. But certainly, you know, if you try to understand equivalences, you use generators if you want to classify all functors. Yeah, so this categorical NC geometry is coming from this Bondal philosophy. Which says that a categorical non-commutative space, I'm going to do everything over the complex numbers or over field of characteristic 0. So a non-commutative space over the complex numbers is just C-linear triangulated or DG category triangulated DG category, let's say, that has all colimits. And so the notation that I'll be using, it's not the standard notation we use, but just for a shortcut, d of x will be the category, and x will be the non-commutative space. So the space will not be there in general, but and so the typical examples, of course, are for a complex scheme. So the typical examples that we've all seen, right? If X is a scheme over C, then you take d of x to be a DG enhancement of the derived category of quasi-coherent sheaves. And if you have an infinity or a DG algebra over the complex numbers, then you take d of x. So x is going to be formally the spectrum of that algebra. I don't know where to write non-commutative, maybe on the spectrum. That will be the category of semi-free modules over that algebra. And so there is a notion, so I'm not going to go into the details of the theory, but there is a notion of maps for non-commutative spaces, which is just morphism between non-commutative spaces are given by triples of adjoint functors corresponding to the pullback, push forward, and compactly supported pullback. And the main thing that I want to recall is the Bondo-Vanderberg theorem, which says that if we have a separated scheme of finite type, then it has a generator. So it says that for every closed subscheme, this DG enhancement of the category of sheaves on X with support on Z, so the full subcategory of sheaves with support on Z is a non-commutative space which is affine. So it is given as the semi-free modules over some DG algebra. And so the problem is that this is not going to work for schemes which are not quasi-separated or are not of finite type, and you would like some substitute for that if you want to understand equivalences and if you want to understand gluing. And the main tool, so what we really want is we want to extend this to some understanding, algebraic understanding of, all sheaves. I mean, all sheaves are a particular example, right, supported on the whole scheme, or sheaves with support on some closed subscheme when X is not quasi-separated or a finite type. Or is analytic or something like that. And so the main tool is something that actually was proposed a long time ago, but wasn't really pushed to its natural conclusion by Kuntsevich and Rosenberg. And it's the fact that non-commutative spaces can be really described by non-commutative localizations. So let me say what that means. So it's a particular type of morphism between differential graded algebras. So a morphism of DG algebras, let's call it phi from A to B, is called a non-commutative localization. If you look at the multiplication map on B as a map defined linearly or bilinearly over A, if this map is a quasi-isomorphism. And this is in the category of B bimodules. And so the model example is the usual recallment of a scheme out of an open and a closed. So if we are in this situation, so separated finite type scheme, and you have a Zariski closed subset, and you have its complement, and so let's say this inclusion map as the standard notation is called J, and this inclusion map is I. Then then you have a recallment triangle where we have the category with supports, we have the category on the whole space, the category on the open, and we have maps. So if you view those as non-commutative spaces, we have maps between them. We have the triples of adjoint functors. And this is a semi-orthogonal decomposition of this category into this piece and this piece. If you take a generator for x so if A is a DG algebra given by, say,
In that example, which one is the NC localization? Which ones are NC localizations?
yeah, I'm
Another question. The pullback map sends what to what? I upper star.
it's probably have them reversed.
You need two arrows this way and one arrow. So two arrows this way. One arrow.
Yeah, they were. Yeah. So if A is the DG algebra computing d of x, then J upper star of A is a generator for so J upper star of A, this is on, it's an algebra object in the derived category of sheaves on U, and the natural map, and this, the endomorphism algebra of this guy is a generator on U, and the natural map that goes from A to B, which is the home from J upper star of A to J upper star of A opposite. This is a non-commutative localization. So it corresponds to a morphism of non-commutative spaces, which is the pullback from X to B to U.
Will this always be a generator?
If A is a generator for X, yeah, it's a generator on U. And so the virtue of this non-commutative localization, I mean, why is it useful, is that, so the basic construction here is that if you have a non-commutative localization, then you get a natural subcategory in the category of A modules, which is everything that's annihilated by B. I mean, in the homotopical sense. And so this has all co-limits. So it gives you a non-commutative space. But in general, doesn't have any compact objects. The only natural object in there is the cone of the map from A to B, and it's not compact. So it is a natural non-commutative space, which in general may not have a generator, may not be affine. And so, of course, the standard example is going from a scheme to an open subscheme. So you can take A to be the affine line, and B to be the algebra of functions on the punctured affine line. So that's a perfectly reasonable example of a non-commutative localization. It's just localization in the ordinary sense with the stupid generators. But the same exact thing works on the affine line if you localize at any number of points. And those points do not need to be countable or discrete or anything. So if you choose any subset in the affine line and you localize in that subset, and you remove that subset, you get a non-commutative localization which is algebraic in this sense. And so as I said, this formalism is useful because it has essentially all the properties. So it describes this new non-commutative space, which may not be geometric or algebraic in the usual sense, but all the standard invariants you would like to have for that space you can construct. So it has many very useful properties. So if A going to B is a non-commutative localization, then, of course, the corresponding map on the opposite algebras is also a non-commutative localization.
But in this case, you do have generators, right? If you just take the sum of all compact objects.
Where? Here?
In both of these cases.
No, here you don't, because S is arbitrary. It may have accumulation.
I see. So it might not be compact.
Yeah. It's not discrete. It's not even locally compact in general. So if you have two non-commutative localizations, so then you look at the products of the corresponding spaces and you get a non-commutative localization. So the map from A tensor A prime over the cone to the cone of A tensor B prime plus A prime tensor B to B tensor B prime, well, shifted by 1, this is a non-commutative localization. In this Recoman setup, this just means if you have an open inside x1 and another open inside x2, then the map from u1 cross x2 union u2 cross x1, x1 cross u2 to inside x1 cross x2, this is a localization. So this is the non-commutative version of that. So this is just to say that it respects products in the non-commutative world. What's more interesting is that it gives you a description of Fourier-Mukai functors. So the co-limit preserving functors from these new spaces between these new non-commutative spaces. This is another space arising from non-commutative localization. It's the space corresponding to this guy. So you have A op tensor B prime plus B tensor B op tensor A prime mapping to B op tensor B prime shifted by 1. So and I'm not going to write it, but you can define Hochschild homology and Hochschild cohomology of these spaces. Even though, so you can define them algebraically without having the generators. So,
So how do you find, well, the Hochschild homology is just defined because it's a subcategory, A mod.
right, but you know, in both cases, they're just given as either tensor product or R homes of the cones of the maps from A to B over A prime tensor A. But yeah, you're right. Hochschild homology.
Well, so then it's not clear that it's the same as the Hochschild homology of CAB as an ordinary category, right?
No, it's not. That's the
It's
point.
not.
Yeah, the point is that it's a definition that actually is consistent with the deformation theory, and it's a definition that's consistent with the de Rham cohomology when it is usual vocalization in the case of schemes. But in general, it wouldn't make sense as a category. Yeah, so if you started with A and B, and you deform the non-commutative focalization morphism, then this Hochschild cohomology will compute the deformations of CAB as deformation coming from the non-commutative focalization.
Sorry, so you were saying there's a different definition of Hochschild homology and cohomology of CAB,
Yeah.
which agrees with the Hochschild homology and cohomology of DZ of X when we're in
When it makes sense,
when it
but
makes sense.
it's a different definition than just the categorical definition. And it really uses, I mean, you know, as I said, what it is, it's just R home from the cone to the cone, or the tensor product from the cone to the cone. Okay, so this is the technique. Of course, you know, for this technique to make sense, you need to somehow get these non-commutative focalizations from somewhere. Not just when you're doing recombinant, but for example, when you're doing descent in the ordinary sense. And so this is what I'm going to talk about now. And of course, you know, once this works, once you can express ordinary gluing of categories of sheaves, DG categories of sheaves, in terms of non-commutative focalization, then that would make sense in the analytic case or in cases where the categories come to you from some non-commutative geometric construction, like mirror symmetry. Okay, so the key remark is that if you take, so if X is just a scheme, ordinary scheme, again over C, and E is a quasi-coherent, E is a sheaf on X, then we have a notion of descent which says that sorry, pre-sheaf. On X, then we have a notion of descent which says that E is a sheaf if we have effectivity of descent data. If systems of local sections of E, which are compatible on overlaps, glue uniquely into a section. So this works for arbitrary sheaves, right? Sheaves of sets, even sheaves with values in infinity categories, you know, anything that has reasonable homotopy theory. So that's the usual notion of descent. So this notion of descent doesn't really translate into non-commutative localization. But there is a kind of a dual notion of descent for sheaves which are quasi-coherent sheaves of O modules. So usual descent requires effectivity of descent data on flat or Zariski covers. Say Zariski covers. Okay, so, but this works for arbitrary sheaves, and the non-commutative focalization is really something that uses a slightly different notion of descent, which only works for quasi-coherent sheaves. And this is what it really encodes in the non-commutative world. So if E is quasi-coherent, pre-sheaf of all modules, there is a different sheaf condition that we can write. So it really works well for good covers. And so a good cover so if X is a scheme, a good cover, I'm going to call it U beta with beta in some poset P by Zariski opens is a cover such that each of those guys is affine. The inclusions are compatible with the partial order on P. And then there are two conditions that these guys satisfy. Condition one is that it's a cover. And condition two is that the local nerves of the cover are contractible. So it says that for every beta 1, beta 2, the intersection of the two opens is covered by everything that's smaller than beta 1 and beta 2. So this property, so for instance, you can take all the affine opens ordered by inclusion. But this property guarantees that if you take the star of every point, so for every close point in X, the poset which consists of all beta in P such that X belongs to U beta, this has a contractible realization. So now, if you have a pre-sheaf of all modules on X, once you fix the cover, you get a collection of modules so the sections on each open, and they have the property that they come naturally equipped with maps, so they're modules over the sections in the structure sheaf. And if you look at the tensor product of those going from one open to another. Then you get a natural maps. And of course, if the sheaf is quasi-coherent, these maps are quasi-isomorphisms. If the pre-sheaf is a quasi-coherent sheaf, these maps are isomorphisms. Or a complex of quasi-coherent sheaves, then these are quasi-isomorphisms. And in fact, so you can define an index category A such that the objects are given by the poset and the homes are just given by the functions on the bigger open.
Above you mean for beta prime less than beta?
Yes. Well, beta prime bigger than beta. Yeah. So beta less than or equal to beta prime, and 0 if beta is not beta prime. And so what these guys are, they're just, so you get these combinatorial models for pre-sheaves, which are just modules over this category. So they're functors from this category to complexes. P was the poset that labels the cover. This depends on the cover. So this is a combinatorial category, depends on X and the cover. And so you can, so you can define these combinatorial pre-sheaves and combinatorial quasi-coherent sheaves. These are just the A mod guys. And then you have quasi-coherent sheaves, which are just the pre-sheaves, is the full subcategory of pre-sheaves for which these maps are quasi-isomorphisms. And now it's not very hard to actually check that. So they're natural functors from pre-sheaves of all modules and quasi-coherent sheaves to combinatorial pre-sheaves and sheaves. And you can check that the derived category of quasi-coherent sheaves goes to these combinatorial sheaves in a quasi-equivalent way. So there is a little bit of technicality there because the natural functor that goes in the opposite direction actually doesn't go to quasi-coherent complexes. It goes to all complexes of all modules, and then you need to check that the essential image is really things that are quasi-isomorphic to quasi-coherent complexes. But it's not a big deal because the natural map is given by extensions by 0 from the opens. So in any case, there is this description that says that dx is this guy. And so now you can, this was A modules, and you can just introduce the notation, call this CAB. the idea is that you want to say this is a non-commutative focalization picture. So for this, you need to describe the functor that goes in the opposite direction, which is like a shiftification functor. But to answer Daniel's previous question, so you see it's different, right? Because the ordinary shiftification goes from pre-shifts to shifts, but it's a left adjoint to the inclusion. Whereas if it's coming from a non-commutative focalization, it corresponds to the compactly supported pullback in the usual case. So it's the right adjoint to the inclusion. So it is a shiftification, but in this non-commutative setting. And in fact, if you have the left adjoint to the inclusion, you pretty much are guaranteed to have a generator here. I mean, it's not quite true, but it's, I mean, with some finiteness condition. For example, if the cover is locally finite, it's true. Okay, so the point is that you want to argue that this is a non-commutative focalization situation. Well, you know, I stated non-commutative focalization for algebras, but it clearly works for small categories too. So you want this to come from a non-commutative focalization of some non-commutative focalization factor from A to some category B. And the question is, what is this guy? Because what you would like to do in general is these notions of pre-shifts is what you would get from, say, family 4 theory in an SYZ vibration. And you want to produce the shifts by some shiftification procedure without knowing what they are. So you would like to be able to say what B is or what CAB is just starting with the category of pre-shifts. And for this, you need, so for this you really need to construct so there is a natural map going from A modules to which is a right adjoint, goes from A modules to CAB sitting inside A modules. And you know, if it was coming from a non-commutative focalization morphism, this map is not a mystery. It is the tensor product with the cone of the map from A to B shifted by -1. So knowing this map is the same as knowing this guy. And let's call this guy T prime. And so the condition that this thing is right adjoint to the inclusion and describes the category B is just saying that this is a coidempotent comonad. So the problem really boils down to starting with A modules and constructing a functor from A modules to A modules, which is a coidempotent comonad, and in some universal way, so that in this situation it really reconstructs the sheaf guys. It's right adjoint to the inclusion for the sheaves. So that's what we really need to construct. And there is a...
The starting data that we have is full set.
Yeah, the starting data will be a pole set with this good cover. And then for each of those, you're going to assign some algebra. Look at modules over that algebra. And then you want to construct this T prime that reconstructs this shift condition in the case when we're dealing with a scheme. And so there is a key lemma or remark, or I don't know what to call it, which says that if we have a DG algebra and an end functor of the category of A modules, which is equipped with a co-unit morphism to the identity. Yeah, these primes are annoying because usually you write the monad, and this is the dual guy. So the monad is called T, and this is the dual guy. But so if you have such a guy, then if you know that for every module the natural map from the square of T prime to T prime given by the co-unit of T prime, if you know that this is a quasi-isomorphism, then automatically T prime is a coidempotent comonad. So you get an isomorphism of functors from the square of this to T prime. You need to invert it. That gives you the monadic structure, and it's automatically co-associative. So what you really need to do is you need to construct a functor from A modules to A modules that has this property, together with a co-unit that has this property. And okay. I don't think I'll be able to write down the solution in general, because there is quite a bit of combinatorics involved. But let me just talk about this simplest of examples to see that. So there is a universal formula for this functor. That's the point. That's the main theorem. There is a universal formula given by some explicit constants, combinatorial constants. So this, and let me just show you what type of a problem you need to solve in the stupidest case when you are gluing just really a separated scheme. So it's the easiest possible situation. You're gluing a separated scheme out of two affines. X is separate. So X is the union of U1 and U2. And then there is one intersection, which is U1, 2, and it's also affine. So you have functions on U1, functions on U2, functions on the intersection, and you have the restriction maps on functions. So it's really important here that these are Zariski opens, because the thing that makes the whole thing work, so it's really about Zariski descent. It's the property that O12, when you tensor it over O1, you get O12, and the same with tensoring over O2. And so now we have a stupid quiver of algebras, and you're looking at modules. Modules over that quiver. So A mod are just diagrams M1, M2, M1, 2. And I'm going to put dashed arrows. So the Mi are modules over Oi. And M12 is a module over O12. What this dash arrow mean? It just means that you need to restrict before you construct the map. So you're specifying a map after restriction. So M1 dashed arrow to M12 just means that you are looking at a map from O12 tensor with M1 over O1 to M12. And the same for M2. And so these are the presheaves. These are the modules. And then you want to construct the sheaf condition intrinsically without referring to the realization. And yeah, so the sheaves, so these are the presheaves, and the sheaves are guys like that so that these maps are quasi-isomorphisms. So what we're trying to do is we're trying to construct a functor T prime from A modules to A modules so that on sheaves, it sends everything to sheaves. On sheaves, it's the identity. And it has a co-unit so that this property holds. And so the functor is not very complicated in this case. In general, it's quite complicated, but in this case, it's not. The combinatorics is very simple. So if you have M, which is this representation of the quiver, T prime of M is going to be another representation of the quiver, which is a sheaf, and it's going to be well, a complex of sheaves. M1 plus O12 tensor M2 mapping to M12, O12 tensor M1 plus M2 mapping to M12, and then O12 tensor M1 plus O12 tensor M2 mapping to M12. And you know the homological degrees are 0 and 1.
You start by fixing the bottom one by making it a triangle, by noticing that this diagram is contractible right now.
Right.
And then you just fix the.
Right. I mean, this is the only thing you can really write. So this describes the functor. You know, there are maps. Okay. You know, all these maps, which are the arrows in the quiver, and then there are these differentials. That you know, so there are maps that go from this place to this place, this place to this place, and then this way and this way. So there are all those arrows and differentials in the quiver. But what you really need to do is you need to describe the co-unit. And so So yeah, I'm just separating the degree 0 pieces and the degree 1 pieces. So these are the degree 1 pieces, these are the degree 0 pieces. And then there are the maps that tell you that this is a presheaf, that this is a module over the quiver. And so there are these yellow guys. This one, and then there is this one, and then there are these guys, and then there are also the differentials. This is just a pictorial description of the D prime guy, and then there are also the differentials that go this way. And then, in order to describe the co-unit, you need to write an extension of this guy by m shifted by -1. So this is m sitting there. And so you just write down all possible maps that you can have. So you can have arrows in the representation of the quiver. So those are not very bad. They're just going here. But then you can have many pieces in the differential. So there is a piece going here, and a piece going here, and a piece going here. There is a piece going here. So there is no such guy. There is only a guy that goes there. And then there is a piece going here. In any case, so you get 6 constants corresponding to all the dashed arrows, to the differential arrows, and to the quiver representation arrows. So they're the natural maps, and you just take any linear combination of those. And the issue is, when is that a representation of your quiver? So that, of course, it gives you a quasi-isomorphism. And so it gives you a linear system of equations on these constants and a linear system of inequalities that you need to solve. And it's completely unclear that it's solvable, but it is. And in fact, you can write this whole problem for an arbitrary cover on an arbitrary scheme. And if you set it up combinatorially correctly by resolving the quiver has very simple presentation with generators and quadratic relations in all degrees. You can actually write down the system of equations and solve it. And so it works for covers which are cubical. So, for example, for a separated scheme, you cover by an affine, finite collection of affines, so that each intersection of those is affine. But it actually gives you the solution for non-quasi-separated schemes, because if you take any cover by any covering by affine, and you look at the intersections which are not necessarily affine, or not even quasi-affine, you can still look at the derived algebra functions on the intersections and take your quiver algebra to be the combinatorics of the cube with these derived DG algebras put on each vertex. And look at representations of that, and these universal formulas that you write actually give you a strict representation of that DG quiver. And so you get the descent statement. And I'm going to shut up.